So as folks may remember, last week I sort of stitched together two areas of investigation. So I talked a little bit about the Smith and Morowitz approach to the nature and origin of life, and I talked about Mark Solmes's approach to the origin of consciousness. And the thing I pointed out was that in both of those cases, the rho-calculus, or a stochastic version of the rho-calculus, is perfectly serviceable to model the phenomena that they're talking about. Now, and part of the reason I'm making these points is not to say how great the rho-calculus is. Instead, I'm trying to critique the culture sort of one-stop shopping using Newton's calculus. So I think it's particularly fragile to try to fit all of our understanding of dynamics into a single calculus. And so what I've been urging for many years now, about 20 years, is that as a culture, we begin to look at different approaches to the modeling of dynamics and representing that and recognizing that the computational frameworks have come a very long way in terms of being able to model dynamics, and that they do carve up the space in a fundamentally different way. So while vector spaces and modules and things like that put the dynamics all in the morphisms, and the algebraic structure is left separate with computational calculi like the lambda calculus or the pi calculus or the rho-calculus or things like that. The dynamics are lumped together with the algebraic structure. And so, for example, there isn't a good notion of what morphisms should preserve in that setting. And since there isn't such a notion, there isn't currently a good notion of how to provide a category for those kinds of structures. So that makes it clear, that there is a category of vector spaces. There's a category of finite dimensional vector spaces and of infinite dimensional vector spaces, and so on and so forth, right? So those are all structures that are amenable to category theory. But the computational structures, such as the lambda calculus and the rho-calculus and so on, they don't have a good categorical story. And it's because they refactor dynamics differently. And it's because of that, I think it's very interesting to look at how they might approach modeling dynamics. And we see that it's very natural when it comes to modeling phenomena like chemistry and biology. And so the question is it also natural as we go lower in the physical sciences stack? So here I've given an example of about 2/3 of an encoding of quantum mechanics into the rho-calculus. Still some work to be done, some not insignificant work to be done there. But here I want to refresh and revisit notions of location and space. And so I've given talks on this calculus before, but it's worthwhile refreshing and revisiting those in the light of what I've been talking about, how to model dynamics and why the computational calculi give us new insights. So with that in mind, the notion of location as a splitting, as a separation of two things has a long history in mathematics. So data kind cuts, they sort of split the real line into two sections, and the point is the thing that each section, points to in some sense. So everything above the point and everything below the point are pointing to that point. So that's the data kind cuts. And Conway games is another example where this idea is taken quite seriously. This idea of a splitting, and both of these have borne a great deal of fruit. So the data kind cuts allow us to construct the real numbers from the rational numbers, and Conway games have given us access to this whole other realm of quantity and ordinality that we'd never even seen before. So the surreal numbers come out of the Conway games. So it's a very rich idea. And I want to argue that Uwe's idea of the zipper should be seen in this light, since we have a group of Scala programmers here. I won't review the zipper because I'm sure you can just go look at a Scala library for zippers or a Haskell library for zippers. But I just want to point out that the notion of a zipper is fairly general. It's not just about trees. So in particular, if I've got some data type T, then the derivative for relatively well-behaved data types, so data types that correspond to polynomial functors, that means the data type as a functor is differentiable. So when I take the derivative of T, then I get the type of one-hold contexts. And so I can form a notion of location as a pair of a one-hold context and the type T. And so the location is the place where you fit the instance, the sub T into the whole. That's the idea of a location. And so it works perfectly for trees, but it also works for any differentiable type constructor. So the idea is to take that notion of a location and apply it to a process calculus, so that names really are locations, right? So intuitively, names are locations in the sense that they're rendezvous points for synchronization. But in the rho-calculus, that's certainly in the pi calculus, that's very abstract. We don't have a good we don't have a good way to think about how those names might be real locations. Although I will point out that Gardner and Cardelli did a version of the pi calculus where names were vectors. So they had a notion of a process calculus which was in which the things were located in space. But if we want to have the notion of space arise from the process calculus, as opposed to sit on the process calculus, sit on top of a pre-existing notion of space, then we have to do a little bit more work. So here, what we want is that the names of a process calculus really are locations in the sense of the Uwe's zipper. So if we revisit the domain equation, which generates the rho-calculus, so here's a two-level type decomposition of the rho-calculus. So P of X, so you give us some set of names X, and we're going to tell you all the process shapes. So this one is 0 or output, right? An X in a process, or input, a place where you're going to receive the data you receive in the process, or parallel composition, the process par, a process, or a name that you can, which is being uncoded to turn it back into a process, right? So that's the basic thing that's dependent on a name, and the rho-calculus is the fixed point of that domain, type constructor. All right, so R of P is going to be P of R of P. So that means that we're taking quoted names or quoted processes as names. So, and in fact, this is exactly, if you go and look at the sort of simplest Haskell or Scala implementation, it's done exactly like this, right? But now we want to change this idea and turn it into quoted process, not quoted processes, but locations. So as per our previous discussion, we're going to take the derivative of this type. So the one-hold context of this type paired with this type. And then we're going to feed that back into itself. So this is the domain equation. And so I wrote this equation down in 2008, and I'm embarrassed to say I couldn't find a decent solution. So you can easily find the syntactic solution, but it's where the syntax interacts with the dynamics. In other words, what's a decent synchronization? What are the COM rules? In other words, for that make this syntax pop. So it took me quite a while to find the sort of the simplest calculus I could find that does the trick. So again, you might be asking, well, why is it that we want an equation like this? And I kind of foreshadowed this in the answer to that question. The intuition in Einstein's field equations is that when you start to take the dynamics into account, here's the field equation. R is the Ricci tensor, G is the metric tensor, and T is the stress energy tensor. And when you start to take dynamics into account, then the metric tensor and the stress energy tensor are recursively intertwined, right? So initially, the stress energy tensor is saying where the matter and energy is distributed, and the metric tensor is telling you where everything is located. But because the stress energy tensor is distributing the matter and energy, that warps the metric tensor, right? So this is going to start telling things to move, and once they've moved, well, that then gives them new locations. Once they have new locations, then that affects the distribution of the matter and energy, and around the loop you go, right? So this is what gives rise to a lot of the dynamics of space-time. So we can get a discrete version of this idea of this recursively intertwined relationship between the metric and the stress energy tensor by linking the dynamics of synchronization to a notion of location. But in order to make this work, we need to add one more ingredient, which we're going to borrow not from physics, but from chemistry, which is the idea of a catalyst. So we're going to have a catalyst that enables the COM rule. So the ordinary COM situation is not going to reduce, but when you have a third ingredient, that will allow it to reduce. Now, strictly speaking, the calculus I will present, it's not a catalyst, because in chemistry, a substance is a catalyst is if it's left over after the reaction has occurred. In the calculus I present, it's not left over. However, there are versions of the I make it so that there's a linear discipline on the substance that enables the reaction, but you could make it so that it's nonlinear, in which case it would be it would strictly conform to the definition of a catalyst. I want to take a quick digression through a variant of the rho-calculus that does a static version of this. So here's our old friend, the rho-calculus. The two things that we need to know, that in addition to this grammar, we need to know that substitution has a modified rule for this the star syntactic construct. So for the D quote, we need to follow this substitution rule. Now notice that for every context K, so for every one hold context, which is a process where you've got a hole in it that you could replace with another process, you could have a version of the COM rule subscripted by that context, so that when you had the reaction happen, right? So Q is communicated along X being bound to Y. Instead of putting the quote of Q here, you take the context of that. So you place Q inside that context and then quote that and substitute that for Y. So this turns out to have lots of applications. In particular, we can imagine that there's, protocols that we want to impedance match, right? So for example, I have an application that speaks, in packets over TCP. And I have another application that speaks in HTTP, right? So we know how to, wrapper up TCP requests into HTTP requests, and then unwrapper HTTP requests into lower level TCP requests. So K can provide that wrapping and unwrapping. So that's something that K can. This kind of notion of the COM rule can do for us. It also works for error correction. So for example, instead of delivering a single copy of Q, we deliver like 3 copies of Q, so that if one gets lost in transmission, there's still 2 more available. So error correcting codes fit within this framework. Notice also that this is compositional, right? So if I have a COM K1 and a COM K2, I can build the composition COM rule, which just composes the context, right? So all of this is very nice, and it gives us a notion of morphism for variants of the rho-calculus that are, that have this context. So you can build a category this way. So that begins to address what I was talking about in terms of categorical accounts of some of these computational calculi. But the main thing is that this is static, right? So it doesn't reify the notion of context enough to give me a notion of location, right? So I need the context to be first class in order to get a notion of location. Here is the calculus. So I've marked in red the variation from the rho-calculus. So we have a notion of a location update, which will be understandable once we go down to the COM rules, and we have a notion of a catalyst, a COM catalyst. And then I should have marked this as well. This is also new. So names are quoted pairs where K is a context and Q is a process. And then a context is given this way, right? So here's the grammar for context. It's basically what you expect. It's a one whole context. And then when we do substitution against a deref, instead of producing Q, we produce K of Q, right? So this is the generalization of the K COM rule that we just talked about. So now here, these first class catalysts are required to make this run. And why is that the case? Well, the reason that's the case is because if you just have a Q, we don't have enough to form a name to substitute for Y, right? A name requires both a context and a Q. And so we have to pick up a context. and we pick it up from the environment, right? So we have some com k floating around. We grab that catalyst from the environment, and then we connect it to the Q, and then quote that pair, and then that's what's substituted for Y. Now, the other thing that's interesting is that you can also disassemble these things, which are waiting to be bound. So in particular, you could, so if you have a top level in the rho-calculus, if you have a top level one of these, it's inert, right? The only time that you can, this is dynamically interesting, is if it sits under a for comprehension which binds it, right? Because if that happens, then it can be subject to a substitution, and so you can get some process here. But in this setting, these things are no longer inert, right? So in particular, you have these location updates, which can grab one of these, right? So these are frozen locations, and disassemble them and turn them into a com catalyst together with an output, right? So I've got a Q, I've got an X, so I can make an output, and I've got a K, so I can make a com gadget, right? And so this, when these two interact, they can produce this, which then can potentially enable another data exchange like this. So any questions so far? Really? It's all super clear?
Well, I'm wondering, I mean, from an application perspective, when we talk about understanding the emerging space, are we talking about that space as being some kind of related things together? Say, for example, discovering the category of something or whatever. Or are we saying something different?
This is really space, like as in data structures. But now the space where you get located is you become a subterm of some context. So maybe an example calculation would help. So suppose that we have this very simple process, right? So on this, so this is going to be, this is a variable effectively, and this is the smallest possible name. This is the first name, right? We've got the zero process and the empty context. So we're listening on this name, and then we're going to drop this here in parallel with, so this for comprehension is running in parallel with sending P on this name, and it's enabled by the com K1. All right, so notice that effectively P is sitting at this name. So you could think of this as like an ambient, right? So P is sitting inside this ambient. And now we do a we do this reduction. So what happens is we pull the K1 out of the com thing, and we wrap, oh, this should be K1, not K prime. Sorry, my mistake. And we wrap, and let me fix that now. So grab that. Okay, so we wrap P up together with K1, and we're going to substitute that for this in this expression here. Well, per our substitution rule, which is this one, whenever we have this thing, one of these for a Y in an expression where Y is starred, we get K of Q. So here, this is the Y with a star on it, so we get K1 of P. Now, if K1 is similarly of a form like this, right? So it could have some other junk in here, but and that's what the dot 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 is for. Now we've got a com K2. So then, and if K2 is also of the form with a K3, then what will happen is P will continue to move. So it will move through space. So it starts off located here at this name, and then it's located inside K1, and then it's located inside K2, then it's located inside K3. So we can think of P as an object moving in space, where these are the different sort of snapshots of where it is in space. And the time is what is moved forward by these com rules, by these interaction rules. So we can describe things like trajectories, right? If you think of P as like a football, and each of these K1s as snapshots of where the football is as it's moving, as it gets passed from one player to another, right? So these Ks would describe the positions of the other players. Does that make sense?
Yeah. Mm-hmm.
Cool.
Thank you.
Sure. No, it's a good question. Go ahead.
So we are basically spending this K1, K2, and K3 for each move, right?
Yeah.
Mm-hmm.
Yeah. Basically saying where you can now begin to describe things like differential equations, right? Because you can say what the configuration needs to be, where P should, what kind of configuration P should be at time 1, what kind of configuration P should be at time 2, and so on, right? So you can begin to describe these sorts of space-time relationships. So you can do physics-like things. But so just a final point. So this represents a discrete version of the intuition's underlying general relativity. It's definitely not quantum as far as my calculations have revealed to me. So there are no non-local correlations in the same way that we get with, the Bell's inequality sorts of things, which, have been tested in the lab. So we know that there's something decidedly non-local going on with quantum mechanics. I mean, you can quibble about the you can quibble about the semantics of that, but it's all it's it's hard to avoid using the language of non-locality when dealing with the Bells, these EPR pairs. But on the other hand, as I've pointed out, we have about 2/3 of an encoding of quantum mechanics into rho-calculus. So it is at least conceivable that encoding can be composed with the techniques that we've described here to get a quantum version of this notion of space. So that's the idea. Again, I'm not saying that this is rich enough to do modern physics problems. I'm suggesting some techniques for how to get to something that's rich enough that to do modern physics problems. And the point is 400 years ago and Newton was just starting out, and so figuring out how to do things like the influence of the moon on the tides took a while. So similarly here, it takes a while just to get the intuitions as to how to think about space in this context. But once we have it, then beginning to do those kinds of things, I think will go considerably faster. And I'm quite interested to see how this compares to what Bob Kuka has done in terms of his, located mobile agents. That should be also interesting. So any additional questions?
I
So
have
in
a
the,
question.
Go ahead. Please, go ahead.
sure. So my question is, in the COM rule, so what happens if we, we have multiple candidates of K, we can do the COM rule. You can apply the COM rule. And if that happens, that means, the evolution of this dynamic system can be non-deterministic.
That's correct. Just like in the rho-calculus. The rho-calculus is also non-deterministic. Yeah. And you can imagine that you do the things are more located. So you can give this greater specificity by having it take an X as well. Right. So if the COM takes an X, then you'd have much greater specificity. Right. So it would still be non-deterministic, but you would have, it'd be targeted more. Good question. Tomislav, you had a question?
Yeah, I have a question about quantum mechanics in rolling. And you said, I mean, do you mean on quantum teleportation that is something that is difficult to model?
At the current time, yes, quantum teleportation is not straightforward, right? So if you look at the encoding of quantum mechanics into rho, that's something that getting that to the point where you can represent quantum teleportation is it's definitely not there yet. Yeah. And
may I ask you about quantum teleportation? How it works? Is it the case that the state that we are transporting is not known for the one who is sending this information?
Is not known for, you'd have to describe the experimental setup in a little bit more detail.
For example, if Alice is trying to teleport something to a Bob, and so this means that Alice has entangled a qubit with the Bob, but also she has their own qubit that she wants to transport. And so I'm not sure if Alice knows the information of the qubit that she wants to send to Bob.
Doesn't necessarily have to know. It's like she can, so this is, in fact, the fact that she doesn't know is what is at the heart of Vigner's paradox, right? So in Vigner's paradox, you have Alice and Bob and Charlie and Danielle. And, Alice and Bob are observing Charlie and Danielle. And so there's this problem where, at one point, Alice knows something about the superposition because she's made a measurement, but Charlie knows something about this superposition because she's made a measurement, but Alice doesn't know. And so therein lies some very interesting paradoxes or challenges for quantum mechanics. And in fact, this has been made experimentally sharp. So there are no-go theorems related to various interpretations for quantum mechanics that are directly come out of the Vigner's paradox. But the short answer is she doesn't have to know. She can make a measurement later.
So you're saying that she can know even without communication with the Bob.
She can know by making a measurement, right? So she'll make a measurement and she'll know what Bob will see once she's made the measurement.
Oh, I see. I have a difficulty to understand why it's not possible. So she needs to send these two classical bits to Bob so that Bob can do the flip and Z gate. And I'm confused if she can send some information somehow, you know, so why is it not possible to send these two bits, classical bits, together with the information that she is sending with the qubit?
That's a slightly different setup, but my recommendation, if you want to understand this very clearly, Bob's book with Alex Kissinger, Picturing Quantum Processes, clarifies the whole thing. So he's got a diagrammatic notation which completely clarifies the quantum teleportation.
Okay.
Yeah.
Okay. Thanks.
It's super clear. Yeah. Yeah. And so in that particular, so then what I would recommend as a methodology is whatever experimental setup you'd like, model it in his notation, and then it should be crystal clear for you what's possible. Because the rules are very simple then, yeah, in the diagrammatic notation.
Usually people don't talk about like very simple case. For example, if we have entangled qubits, and can I detect if you did with your part of the qubit something or not? I mean, this is like the basic, right? Because if we can detect if someone can do something, this immediately creates some channel of communication.
Yes,
so I suppose this is not possible, right?
That's not possible. What you can do is make a measurement, but you can't tell it. The measurement doesn't tell, like knowing that the particle is spin up doesn't tell you whether or not your counterpart already measured there's a spin down.
I see. Because because I was thinking if we can detect that someone eavesdropped the qubit, I was thinking this is also like channel of communication. So must be something.
There's no experiment that I know of that would reveal that, right? All you can do is check to see whether the particle is, you know, in a particular state. So, or the quantum, yeah, you can make an observation of the quantum state is really the idea. But I mean, I'm certainly not an expert on quantum mechanics or quantum information, quantum computation. So I only dabble in it. But definitely we don't have these non-local correlations in this setting. So that would have to be further elaboration. But that said, I still think this is a pretty cool calculus. I think the calculus itself, you know, as I've already shown here, this has lots of applications. So I came up with this when I was thinking about the sort of butterfly wing hurricane problem that shows up a lot in biology, right? So in biology, you have these phenomena that are crossing these massive time scales, right? So the signaling that's happening in the cytoplasm is happening really fast, like blazingly fast, like, you know, femtosecond fast. I mean, that's an exaggeration, but it's super fast. Whereas what's happening in the nucleus is happening like on the scale of seconds or minutes. And so, you know, like the differential equations are particularly brittle with that many orders of magnitude difference to try to model the behavior. And here, you know, the idea is that you can put some kind of impedance match. And that turns out to be useful, in lots of places. It's useful for modeling biological phenomena, but it's also useful for modeling, internet protocols and error correction and lots of stuff. And it's compositional, right? So this is clearly useful. And all this does is to make that thing programmable, right? So I can now, instead of just having a static, instead of having a static K for all COM events, right? I have dynamic Ks for different COM events, which allow me to have to program which Ks I want to be influencing the interoperability or error correction or impedance matching. So it's already useful in that sense. So there's a reason to study this kind of dynamics, but the point is that at least intuitively we can now start to wrap our minds around how you would locate things in space, where the notion of space and time arises from the dynamical picture. Well, thank you very much. Unless there are any other questions, we can yield back 16 minutes, and that gives me a few minutes to prepare for the call with Magnum.
Great. Thanks, Greg. We appreciate it.
Thank you. Ciao, ciao.
Thanks.
Thank you.
Right.